One typical collision discussed in Physics 1 is elastic collisions. And by definition, an elastic collision has no loss in energy. This yields a unique derivation combining both conservative quantities, the momentum of a system and the energy of a system, that actually breaks down to be a very useful shortcut. And I'd just like to show you that here. One thing at the top, though, that we must say is this only works if the masses stay constant. In other words, ball 1 has a set mass, whatever it is, and ball 2 has a set mass, whatever it is. When these things collide, those two objects cannot break, combine, or change their mass in any way. So assuming mass, the masses do not change. If we assume the masses do not change, there are two conservative quantities, both momentum and energy, because by definition there is no loss in energy. So the first one should be fairly familiar. That's to look at it from a momentum perspective. As we've seen before, the momentum of a system must be equal to the momentum of the system afterwards. And when we break these down, we would say that this is the momentum of ball 1 plus the momentum of ball 2 equal to the momentum of ball 1 plus the momentum of ball 2 after their interaction. Expanding out the fact that momentum is mass times velocity, this becomes m1 v1 plus m2 v2 equal to m1 v1 prime plus m2 v2 prime. Again, the masses do not change, so they don't need prime notation because they're the same value. Now, planning ahead for what we're going to use this for, we're going to rearrange a little bit to group like terms in terms of the masses rather than before and after. So if I subtract m1 v1 prime to this side and I subtract m2 v2 original to this side, then this says m1 v1 minus m1 v1 prime equals m2 v2 prime minus m2 v2. And we did this basically because we'd like to factor out the mass. So that makes this m1 times the quantity v1 minus its after component equal to m2, which is multiplied times v2 prime minus its original component. That stages up for the next step, so we'll come back to that in just a moment. We'll define this as equation 1, which is derived from momentum. Now, from the energy perspective, we know that E equals E prime. And so again, regardless of what's happening in this particular system, we have the kinetic energy of the first object plus the kinetic energy of the second object equal to the kinetic energy of the first object after the collision plus the kinetic energy of the second object after the collision. Again, there are no other energy terms because the two balls are either moving or they are not moving. There are no other options. Now, expanding out the formula for kinetic energy, I have 1/2 m1 v1 squared plus 1/2 m2 v2 squared equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Now again, the halves are common to all terms, so we can drop those out. And then we're going to do the same operation we did before, which is combining like objects as opposed to their before and afters. So if I subtract m1 v1 prime squared to this side and dropping all the 1/2s, then I have m1 v1 squared minus m1 v1 prime squared equal to m2 v2 prime squared minus m2 v2 squared, which is a similar operation to what we did on the in the momentum. So then we're going to take this statement and factor out the m's. m1 times the quantity v1 squared minus v1 prime squared equals m2 times the quantity v2 prime squared minus v2 squared. Now, that doesn't seem very useful at first, unless you pay attention to the fact that this statement, and on either side, is actually a difference of squares. And so if I were to reverse the difference of squares, I could expand these statements to be m1 times a quantity v1 minus v1 prime times a quantity v1 plus v1 prime. And you can see that if I FOIL this out, I would get back to this up here at the top. Doing the same thing on this side, I have m2 times the quantity v2 prime minus v2 times the quantity v2 prime plus v2. If we stop here and define this as equation 2, then because the conservation laws hold true for both statements, if I take equation 2 and divide by equation 1, in other words, a system of equations eliminating some common variables, then mv minus v prime, mv minus v prime, and m2 v2 prime minus v2 is here. And so this whole section of this side and this whole section of this side is derived in the momentum. So when I divide equation 1 from equation 2, that all drops out. And so what I end up with is a very clean statement that states v1 plus its after component is equal to v2 prime plus its before component. And obviously the order of addition does not matter. And so what this statement says is that for an elastic collision, the velocities of the objects can be thought of as a before and after for v1 being equal to the before and after for the second object. In other words, the mass does not matter and the velocities are conservative. So in an elastic collision, and this is only an elastic collision where the masses do not change, elastic collision, the velocities are conservative.